I could.
Okay, let's get this thing started. Are we ready?
Yeah.
It is a pleasure to welcome, introduce Sean Lewis. Sean's been working with me and Mordecai on the Torch project, which is kind of began as a Drexel project some years ago with Josh Wall, and has blossomed into international collaboration. So Sean has made quite a transition. Sean has made quite a transition on this. He started off basically as a user of a package. Did some very interesting work, and then made a significant diversion in the software development, which has been a major contribution to the package, and I think developing a whole direction for the entire project. The context for Torch and for Sean's work is on star cluster formation and feedback from stars. His thesis is new perspectives on the formation and early evolution of stellar clusters. Okay, Sean.
Thank you. Yeah, thank you, Steve, for that intro. So yeah, welcome to my thesis defense. Today, I'm going to be talking to you about some new perspectives I'm providing on the formation and early evolution of stellar clusters. Okay, good to go. Great. Yeah. So in our galaxy and others, there are stars. Stars form from collapsing clouds of gas and dust. And within these star-forming regions, the majority of stars are forming in clustered environments, star clusters. The nature of star clusters and the processes by which they form, the environments from which they form from, and the evolution of that environment all remain active areas, active domains of study in astrophysics. I should say, so this is one such cluster. This is called Westerlund 2. Zoomed in here, if you look at a higher resolution image of this. Aside from being just a nice picture to look at, it's a Hubble image. I think this particular cluster does a good job at showcasing the different regimes of star cluster formation that are critical to the process.
Can I ask, can you outline what the cluster is actually?
Sure, yeah, so it's a little, I mean, by eye, it's perhaps a bit difficult, but you can see like the main collection of stars here would be the cluster. I mean, in the actual observational surveys, you have a little bit more information, so you can look at the emission lines of all the stars that are present and see if they have like a bulk velocity that's
because
similar.
it looks to me like if you just look at this image, it's really difficult to say what the cluster is.
Certainly, yeah, and there's like, you know, some stars are maybe foreground stars are much closer. This cluster is 20,000 light years away, so it's far. So there's stars between us and it. So yeah, some of these are foreground stars, but some of them, like this here, is a binary Wolf-Rayet. What's called a binary Wolf-Rayet star system. So that's within the cluster. Yeah, and if you have, by the way, if you have any questions that are critical to sort of understanding what's going on, do ask them. But otherwise, write them down and save them to the end so that we can. I don't go too overtime because it does cut it a little bit close. Okay, great. So we're looking at the different regimes of regimes that are important for star cluster formation. So we'll start looking at the gas. So we have a scale on the bottom left that's approximately 1 parsec. Parsec is 3.3 light years or so. And so fairly large, but the gas for star cluster formation, refer to it as the interstellar mediums. It's the material in between stars. The interstellar medium has different categorizations based on its physical properties. So we have the cold neutral medium, which is the densest of that gas. It's cold, as the name implies, typically below 100 Kelvin. There's also the larger complex, subcategories of cold neutral medium, larger complexes of gas, which are called giant molecular clouds. Those can be dozens of parsecs wide or larger, between 1,000 and thousands and millions of solar masses of material. That's hydrogen gas, hydrogen and helium mostly. By the way, when we talk about masses of objects in astrophysics, we typically relate it to solar masses. So one solar mass is the mass of our sun. So giant molecular clouds, thousands or millions of solar masses. There's also smaller substructures we call cores, gas cores, which are fractions of a parsec in size and a few solar masses to a few hundred solar masses. So in this image, the kind of darker clumps of gas that you can see here, examples of those cores. There's also what's called a warm neutral medium, which, as the name implies, is warmer. So it's 10,000 Kelvin in temperature. It's less dense than the cold neutral medium. This warm neutral medium, cold neutral medium intermingle, and they're able to exist simultaneously together. There's other regimes of the interstellar medium which are important to, or I guess related to star cluster formation. There's shocked gas, so gas that is actually mechanically impacted, and it will heat up to millions of Kelvin temperature. There's also ionized regions of ionized gas, ionized hydrogen, which are called H2 regions, which is less dense and several thousand kelvins of temperature. And these two regions are important because they're related to, or they're directly resultant from, interactions of between the stars that have formed from the gas and the gas itself. So stars, as we'll talk about in a little bit, have these mechanisms of feedback, which interact with the gas from the form. So let's talk about the stars a little bit more. Stars come in many different masses, and the stellar mass is what dictates many of the properties of the stars. So like the luminosity, how bright it is, how much radiation it's emitting, and the star's lifespan. And so the majority of stars are on the order of or less massive than our sun. They are cooler in temperature, their color, white, yellow, red. They live much longer and fairly stable lives, at least compared to the others we'll talk about. We're talking several billions of years as a lifespan. On the other hand, there's very few high mass stars or very massive stars. Although they're few in number, they dominate the luminosity of a single cluster. So just a handful of stars can contribute a majority of the radiation coming from a single cluster. They burn much hotter, they're brighter, they're typically blue in color, they are blue in color, and they live much more violently in terms of their interaction with the environment from which they form, and just a fraction as long as lower mass stars. So very massive stars live only a few million years. Low mass stars live for billions of years. And so just to kind of show an analytical example of this, or a database example of this, this is showing a mass function for the cluster we were just looking at. So on the x-axis, it's the log of the stellar masses. So that means that the 0 on the x-axis is talking about 1 solar mass. And then on the y-axis is a scaled number of stars. So you can see stars that are to the left of 0, left of 1 solar mass, means stars less massive than our sun. There's much more of those than there are stars more massive than the sun. And very much so for the highest mass, or the furthest right on the x-axis, the fewest number of stars, those very high mass stars that contribute the majority of luminosity and feedback to a star cluster system. Clicker is not working. Okay, the process, star cluster formation process. This is a good sort of cartoonish example of how this functions. So we have a gravitationally collapsing giant molecular cloud. And as this cloud collapses, it'll hierarchically fragment into subclouds, which then continue to collapse and eventually form stars. Those stars that form, some of those are massive enough to have significant feedback, which ends up dispersing the gas within their general areas. You can see that happening here. They're blowing out little bubbles, blowing away the gas in their vicinity. And those subclusters will, again, hierarchically assemble into single large clusters. This and that. And then the feedback process will continue to blow gas away, ultimately resulting in the end of the formation of this cluster. So take a brief moment to talk about stellar feedback. So the feedback from massive stars, as I said, are mechanisms that are really resulting in the end of star cluster formation. And so the feedback mechanisms that we talk about most are ionization, so ionizing radiation, radiation pressure, Stellar winds, it's actually material being stripped off from the atmospheres, outer atmospheres of the stars and deposited into the environment, and supernovae. So the most massive stars will, when they die after a few million years of their lifespan, they die in supernova explosions. And so this is a collection of observational works that is showing different masses of giant molecular clouds in the x-axis. And then on the y-axis is radii, or the radius of the clusters. And this is just showing the regimes in which the different feedback mechanisms are important or contribute significantly to the evolution of the giant molecular cloud as it forms stars. And so the main point I want to make here is there's a couple of lines that we just mentioned. The ionization, the red dotted line, the direct radiations, radiation pressure, and supernovae, all those with to the up and to the left regions. So a significant portion of the of observed clouds are affected by these types of radiation. Sorry, these types of feedback.
Question.
Yeah.
Where's the cluster that our sun belongs to in this block?
Good question. Yeah. So the our sun is currently not in a cluster. So this is actually, it's from late 2003. They found that the majority of stars, while forming in clusters, the majority of clusters also dissipate, and so ultimately, through various mechanisms, will fragment and dispel their stars to the surrounding region. So our sun is not in a cluster right now, but it was likely at some point.
So that means our galaxy is not part of the cluster.
No, yeah. So the clusters are forming within the very small subregions of the galactic structure. Yeah.
So what's the criteria that you like? If our galaxy is not a cluster, I'm assuming you need multiple galaxies to be in a cluster. So how do you define it?
So within a single galaxy, you'll have giant molecular clouds. So subregions of a single galaxy, you'll have star-forming regions where star clusters can form. So this is all
I see. So these star clusters are actually smaller.
Correct. Exactly. So,
Okay.
yeah.
Sorry,
No,
thanks.
it's a very good question. Yeah, because the terminology is similar. So the cosmologists typically, or galaxy, people say galaxies will talk about clusters, but they're referring to clusters of galaxies, not clusters of stars. So
Thank
yeah,
you.
terminology is the same. Yeah, very good question. Thank you. Okay, so speaking of studying star clusters, there are some challenges that come with studying the process of star cluster formation. That those problems are really twofold. Firstly, the process of a single star cluster forming takes place over several millions of years. So if you're observing a single star cluster like Westerlund 2 that we're looking at before, you can take a Hubble image of it right now. You could take another one in 10 years, 100 years, and they're ultimately going to basically look like the same snapshot. The evolution of the entire lifespan of a star cluster for star clusters takes place over millions of years. So it's really difficult to observe the entire formation process looking at a single cluster. So observationalists will rely on statistical methods, look at several or many different star clusters of similar masses, similar points in their evolution, to make inferences about the star cluster formation process. A second problem is that even if we could watch a single cluster form from beginning to end, the nature of the cluster dictates that they are forming within thick clouds of gas and dust, and those ultimately obscure our view using observational methods. So clusters form in obscure environments, and they take a long time, at least on human scales, to observe. So for these reasons, we need to employ numerical models to really fully study the star cluster formation process. And so I want to talk real quick about the numerical model that I primarily have used for my research. This numerical model is called TORCH. And if you recall what it does is it of course, models star cluster formation. And the main components of star cluster formation, as we talked about, were gas, collapsing gas, and the stars that form from it, and the feedback from those stars. So first, I was taking piece by piece through this numerical model. First, what we're looking at here is the piece of this that models the magnetohyddrodynamics of star cluster formation. That is the gas that's collapsing. So this piece is called flash, and flash, the structure by which it simulates or models the gas collapsing looks like this on the right. So it's called an adaptive mesh refinement code. So it's a Cartesian grid that has these subdivisions of higher resolution. And so as the gas moves around, this grid remains static, but certain portions of it can become higher refined if you have gas that's collapsing in and becoming more dense. You want to resolve it more closely, resolve it before you can increase the refinement at specific regions. And so this is terminology that we'll talk about again a little bit later in the talk, that each of these squares in this computational domain, this grid that again is simulating the gas, each of these squares is called a block. Each of these blocks is made up of cells. And so the cells are actually the data points within this computational domain. And so gas can move through this structure. And as I said, as it collapses, we'll have regions of higher refinement. And as gas continues to collapse, it becomes more and more computationally, or the time step required to resolve the behavior of the gas at smaller and smaller scales drops significantly. So to prevent that from continuing on and on forever, like reducing our ability to model the entire system, we end up replacing the gas in a collapsing region with what we call a sink particle. So sink particles just replace that gas that otherwise would continue to collapse. And we say, okay, this gas now is just represented as a single particle, and we'll instead allow this particle to accrete more material onto it, so more gas can fall into that region. And that accreted material can then be turned into individual star particles. So each of these sinks, when they do form, we give them a list of star masses that it's allowed to form. And as it accretes material, it will begin forming those stars. Oops. So those stars eventually do form and are placed inside of the sink. And so then once we are forming our stars, then we need a way to model those stars. We were just looking at the gas flash. The other piece of torch, my numerical model that I use, is a muse. And so a muse models, or it does a couple of things. First off, it establishes this interface between these two codes. So we'll see in a second, there's communication that's needed to take place between the gas and the stars. A muse also models dynamically the behavior of the stars. The stars can interact with each other gravitationally. A muse also, or I should say, so the stars evolve gravitationally, so they evolve together. They also, through the muse interface, evolve or feel the gravitational influence of the gas modeled in flash, which then can pass that data through the muse interface to where we're modeling stars and vice versa. And a muse also handles the stellar evolution of the stars. So especially for the massive stars that are emitting feedback mechanisms like ionization, solar winds, those processes change over the lifetime of a star. And a muse handles the modeling of that change, including things like supernova. So those stars eventually will die and detonate as supernova. So a muse handles that. A muse then also informs flash about those feedback mechanisms. So if a muse is calculating what the amount of ionization energy that a massive star is emitting at any one time, it'll then pass that information into flash, which we can then model that ionizing radiation through radiative transfers. We'll cast rays out from a region where the star is sitting, which will heat up the gas around it. So it's all modeled in flash. And then from this, we can analyze the results of simulation using this tool. We can look at things like the gas expulsion, so how the gas is removed from a system. We can look at the star formation efficiency, so how much of the original material is converted into stars. We can also look at things like the properties of the star clusters that form, so their masses, their radii, and their structural properties. So I want to talk a little bit about massive stars again. And so there have been numerous studies on massive stars and their the results of their feedback mechanisms. And it's well understood that massive stars are like majorly responsible for, or primarily responsible for the ending of star cluster formation. So they were the reason why gas has been blown out away from the star cluster. Therefore, if there's no gas there, no more stars can form, your star cluster is finished forming. There's been studies that show that how that gas is removed is important. So whether the gas is removed very rapidly or gradually over time. But I identified that there was limited research on the timing of massive star formation. So whether massive stars are forming very early in the star cluster formation process or later on. And so using TORCH, the numerical model we were just looking at, I designed a controlled experiment to study the hypothesis that early forming massive stars were particularly destructive in their effect of, they're particularly destructive in the star cluster formation process. So, like I said, using TORCH, the numerical model I was just talking about, I designed a controlled experiment in which I had four different simulations of the same giant molecular cloud. So starting from the same initial conditions, that is, we had a spherical cloud that had 10,000 solar masses of gas, same velocity dispersion, so the gas is moving in the same way across all of these simulations. The only thing that's different between these four is the first stars that are forming, or that are allowed to form. So in the first simulation, which I refer to as the fiducial run, I allow the TORCH numerical model to proceed essentially as normal, so as it normally would. In which case, stars are randomly sampled and placed when sync particles form, syncs accrete material. But for the other three simulations, I modify the mass list of the first sync such that as it's accreting material, the very first star that it forms is either a 50, 70, or 100 solar mass star. So an extremely large star is essentially forced to form as early as possible. And again, this is starting from all otherwise identical initial conditions. And so then I allow these models to evolve for 4.5 million years. All the while, gas is collapsing, stars are forming, other sync particles are forming, they're forming stars there. Still, a feedback is taking place from those massive stars. And then I analyze the results of those early forming massive stars and their effects on the gas dynamics, the star clusters, and the cluster assembly. So we can look at a video real quick of what that looks like. So you can see on the left, this is our initial starting for our initial conditions. So all four of these simulations would look like this. And you see our spherical gas, we've got 10,000 solar masses of material there. And as I play this video, you'll see the gas start to move around. It's self-gravitating, so it'll start collapsing in on itself. And you'll see sync particles, these are the black points, start forming, low mass stars being modeled or being shown as little red dots, and high mass stars, those with feedback with blue. Yes.
Is this the fiducial?
Yes, yes, yeah. Thank you for reminding. Yes, we're about to see the fiducial run. So if I play this, you see the gas is self-gravitating, it's collapsing, we've got sinks forming, we've got stars forming from those sinks. Little subclusters forming, they're falling in together. Massive stars still form in the fiducial run. Remember, the only difference is that the first star that forms is just randomly sampled. It's not the very massive star like the other ones.
What was the mass of the first star that formed?
Good question. Yeah, so there's in this several, I think several hundred low mass stars, so stars that don't have feedbacks below in this model, below the 8 solar masses. The first massive star that forms, actually, I'll try to rewind this. I don't know if I can. Okay, maybe I'll show later, but it's a 35 solar mass star that forms towards the edge of the cloud.
That's nowhere near as big as what we're gonna.
Exactly. Yeah. And it also is forming towards the edge of the cloud, so its
Has
destructive
minimal
effect is exactly.
I have one more clarification.
Yes.
question. What do you think about?
Good question. Yeah. So the sinks were it's a subgrid model in the sense that when gas is collapsing and we identify regions in which that gas is going to continue to collapse, instead of modeling that continual collapse and that driving down the time step of the simulation, we'll replace that gas with the sync particle, which instead just allows material to accrete onto it, so it becomes more massive, but we don't have to actually model the
Oh,
gas
the
anymore.
dynamics.
Exactly, exactly. And so then those sinks are the things that then are able to
So this
respond.
is just like optimization. of code.
Yeah, essentially, yeah, exactly. Great. So, oops, so we are doing this again. Yeah, real quick, up at the top, you see there's a 35, 37 solar mass star that forms. You can see it kind of blows gas out. But I can put this next to the 3 other runs where I had the early forming massive star. This is a snapshot taken for each of these runs at the exact same times. The same amount of evolution has taken place, 4.5 million years. You can see just on visual inspection, like there's a pretty major difference between these. So this fiducial run, the one we just watched in the top left. Then the 50 solar mass star, you can see the little orange arrow. It's that one right there that formed. The 70 and 100. And so there's obviously an effect taking place, but we need to be able to quantify that a bit more. Oh, yes, and then also I have a density contour map of these same simulations. This is a kind of a rotated side view of the same snapshots here. And you can see the density is looking at the gas. There's more centrally concentrated gas in the fiducial run, especially compared to the 100 solar mass run. We have this little clumps of gas and this void of less material in the center.
How much were these ones take?
Good question. Yeah, so these took several weeks operating on a couple or 24 cores, 24 processors. The couple week time that it takes, ideally, these really should only take like a week, I would think. But there was a lot of sort of fixing problems that come up during simulations, of course, but yeah, several weeks. Okay. So I said we need to quantify this a little bit more. So what are the effects of these early massive stars? So one thing we can look at is the total energetics of the gas in these simulations. So you can see in the bottom left for this leftmost plot, all the simulations, as I said before, are starting from the same initial conditions. So they have this globally negative total energy, meaning the gas is in a bound state, which is what we expect. It's collapsing in on itself. And then at the black arrows around when the early forming massive stars form in augmented runs. And you'll see pretty much immediately the gas achieves a globally positive energy state. So gas has become globally unbound. And it's not until about a little less than 2 million years later that the fiducial run is able to achieve the same state, same unbound state. As there's some fluctuations in the fiducial run. That's because, as I said, there are other massive stars that are forming, but it's not until around this 4 million year mark that a significant star formation event takes place. And there's several 60 solar mass stars that form and are ultimately able to unbind the gas globally. On the right, I'm just showing a sliced plot of the density of ionized hydrogen. So in the regions where it's kind of maroon, there's black regions, this is where there's still majority neutral hydrogen present. So potentially star forming material, whereas all the gas that is colored is gas that has been ionized. So ultimately just showing there's for the early forming massive star runs, they have a widespread significant effect on the gas. Something else we can look at is the cumulative star formation of within these simulations. So on the left, looking at the total number of stars that form, and you can see again, I've marked where the early forming massive stars form around about there. And you see there's a pretty stark difference between the fiducial run, the red line, and the other 3 augmented simulations. So the fiducial run is able to form 2 to 3 times more stellar material than the other runs. And then I also calculate the star formation efficiency for these systems at the end of the simulation. So the fiducial runs converts about 23% of the initial gas into stars, less so for the runs with the early forming massive star. And kind of in a similar vein, we can look at the accretion rates of material onto the sink particles. So how much material are the sinks pulling into themselves, and then what is the star formation rate, so the rate at which stars are placed into the simulations. And you can see similar trends here where the fiducial run is able to, or achieves a much higher sink accretion and star formation rate, whereas in the 50, 70, and 100 early forming massive star runs, that peak is suppressed. The star formation, interestingly, seems to take place over a longer period of time, but ultimately the suppressed star formation and sink accretion rates. We can compare that, the star formation efficiency to observations. So this is just a series of different methods for observing star formation efficiency in clusters. The black boxes that I have here are the ranges in which my runs land. My runs are, yes.
Are you showing epsilon total or epsilon per free fall time, which is what's shown in this plot?
Oh yeah, this is the free fall time.
And
Yeah.
But is your black box your total?
Yeah, you're right. Oh, there may be a mistake on this one. Yeah, I'll have to correct that later.
Yeah.
But ultimately, the main point for this, and I guess described better in my paper, that this falls within ranges that have been observed, and my star formation efficiency fall within ranges that were observed. Another thing we can look at, so at this point we're talking about the energetics of the gas that are in my simulations. We can also look at the structure of the clusters that form. So this is the same collection of simulations, the same snapshot for 4.5 million years, but just without the gas. We're only looking at the stars here. So in the fiducial run, we have a single massive cluster in which 99% of all the stars in the simulation or the computational domain are within this one cluster. Whereas in the other runs, we had the early forming massive star that instead has formed these spatially separate lower mass subclusters that themselves are less, more loosely bound than the large cluster in the fiducial run. And so again, we can compare this to other simulations, and the clusters that form, this is looking at this cluster masses and their radii, are falling within a range that have been clusters that have been produced in other simulations. But ultimately here, the point is that in the early forming massive star runs, we see this destructive effect in the ability for the giant molecular cloud to produce a single massive cluster, as instead promoting the production of these spatially separated subclusters. So to review this, by the way, this is like the first half of my thesis work. I'm going to transition to something else in a second, but to review these points, early forming massive stars, I found that they have a particularly destructive effect, or a particular ability to disrupt the natal gas that they're forming from, globally unbinding the gas prematurely compared to the fiducial run. They suppress the star formation rate and the cumulative star formation. I also find that they disrupt the hierarchical assembly of the final star cluster that is formed. So ultimately, what this is, what I want to say from this is that the timing of early forming massive stars is a parameter that needs to be taken into account in these numerical models. So many numerical models will randomly sample their stars. So which stars form is determined kind of probabilistically. And whether a massive star forms early or late is important due to, obviously, its effects on the star cluster formation process. Okay, great. So that was work from a published paper of mine, first part of my thesis published earlier this year. And I'm going to transition now. It's a similar topic, same topic, but a slightly different focus here. So to introduce this, I want to talk about some of the problems with another set of problems with numerical models, specifically to do with the initial conditions that are used. So for the simulations that we just looked at on the left, we started with perfectly spherical turbulent spheres of gas, showing the velocity dispersion here. So the gas has some movement, but ultimately a perfectly circular, perfectly spherical cloud. And another example of initial conditions from Claire Dobbs's work, having cylinders of gas colliding together to form star clusters there. And these initial conditions are useful for us in the sense that they're very easy to initialize, they're very easy to set up, and they are close in modeling what giant molecular clouds are like in reality. But of course, in real life, we don't actually observe any perfectly spherical gas clouds or perfectly cylindrical colliding clouds. And so it would be ideal for us to be able to use or to initialize our simulations using gas clouds that have formed under more realistic environments. So for example, this simulation work from a colleague of mine, Hui Li, modeling an entire galaxy. So you can see the galaxy swirl here. All of this that we're showing in color is the gas that is present there. And so the clouds that then can be identified out of this galactic simulation are clouds that have formed under a galactic environment. And so they're not perfectly spherical or perfectly cylindrical colliding clouds. They're much more self-consistent in their modeling. So it'd be ideal if we could take one of these clouds and use as initial conditions. And the reason why we aren't able to do that already is it's very difficult for a single computational model, or basically impossible for a single numerical model to span the entire spatial regime between modeling an entire galaxy, down to modeling individual clouds, down to modeling individual stars. The spatial regime is just too computationally intensive. So typically simulation researchers will sort of choose a regime and work within that. So for instance, in this work, modeling an entire galaxy, but then once individual clouds are forming, instead of modeling individual stars, modeling or representing an entire star cluster as a single particle. Or like from the perspective of the work I was just showing of mine, instead of modeling an entire galaxy, modeling a single cloud and then modeling the stars within. So this disconnect between the different regimes that are important in terms of the initialization of giant molecular clouds. And this difficulty is sort of continued, or I guess I should say, like the ideal, once again, is we want to be able to, in Torch, use these molecular clouds that form under more realistic conditions as our initial conditions. And the problem with that, though, is, again, from before, this is an example of how Torch is modeling the gas. So it's that adaptive mesh refinement. We've got blocks, which are made of cells. It's a static grid. The galactic simulation, which you just saw on the previous slide, is modeled using a completely different software suite called Arepo, which uses what's called a moving mesh. The way it works is it has these mesh generating particles, which are able to follow the flow of fluid around. And they, from those particles, generate what's called a Voronoi mesh, which fills in the volume around these particles. And so we want to be able to take clouds, giant molecular clouds that have formed under a galactic simulation, which uses this Arepo data structure or representation for a gas. And I want to be able to use this data in Torch. And the problem is that there's no simple way, or at least not into my work, there was no way to easily transfer data between these two simulations. And so that's where my work came in. So this part of my thesis was developing a tool to do exactly this. And as far as I'm aware, before this work, this process of transferring data from a Voronoi mesh, moving mesh code to an adaptive mesh refinement did not exist before my work. And so I call this tool VOR-AMR, so Voronoi mesh AMR grid, or AMR. And it, as it says, it is interpolates data between or from Arepo Voronoi mesh into Torch. And so I'm going to show a quick diagram to explain exactly how this works. If you recall, we talked about Torch before. So this is that same torch framework. It has Flash, which handles the magnetohyddrodynamics, and Muse, which handles the interface between those, and then modeling the stars and the stellar feedback. And now I have this Arepo data, so this galactic simulation, which has clouds, giant liquid clouds that I want to use as initial conditions. And I want to get this data compatible with the torch framework. And so the way that I do that is first I send the positional information of the mesh generating particles of this Arepo data to Flash, and I send it to Muse. And also to Muse, I send the field value data. So that's like the gas, the data associated with the gas. That's more like the gas density, temperature, or internal energy, velocity, etc.
Just to clarify, those
Yes.
are those values at the particle positions.
At the particle position is where they're defined, and they also are represented across that Voronoi mesh cell that they're generated.
Oh, okay. So you're starting with, okay, got it.
Yeah, but those particles give me a point at which those cells are defined. Yeah. So once I pass this Arepo data to Flash and Muse, I can then I essentially ask Flash to look at the positional information of the Voronoi mesh, of the Arepo data, and Flash constructs a AMR grid, so that refined Cartesian grid, that mimics as best as it can the structure of a distribution of the Arepo mesh generating particles. And at the same time, Muse constructs a k-dimensional binary lookup tree of using the same positional information of the Arepo data along with the gas values. And we'll see how that comes in handy in a second. So then at this point, Flash has this empty computational domain of this refined grid that looks like the same structure as the Arepo data. And then it goes through block by block and asks a Muse to, or rather I should say, sends a Muse an empty block one at a time with empty data cells within that block that a Muse can then fill. And so a Muse will then look at each of the cells within that block, and then using this k-dimensional binary tree, will look up the nearest Arepo data point to each of those cell centers, and it will interpolate data into that. Then through the interface, a Muse then sends that information about that now populated block back to Flash. This process repeats for each block, so there can be thousands or tens of thousands of blocks. So we'll cycle through this, populating the Flash grid, and then eventually Flash will output this populated grid to use as our torch initial conditions. And so I know this is like a lot of words, and hopefully the diagram helped a little bit, but I also have like a visualization that will help help make this make sense a little bit more. Oops. Second. So this is our Arepo data. So you recognize this is our galaxy that was being modeled. Again, this is from a colleague of mine, Hui Li, was at Columbia University at the time. And from this galactic simulation, giant molecular clouds form under these more realistic galactic conditions, and we can extract one of those clouds as the snapshot of data. This is all in Arepo. And so with that Arepo data, I want to then convert this to torch usable data with my Fourier AMR tool. And so to show this, I'll strip away all of the gas, and so we can see the Voronoi structure of this computational domain, saying this is in Arepo. Then I take from this the positional information of the mesh generating particles. Those mesh generating particles, and take those, pass those to Flash, and ask Flash to construct a computational domain, or an AMR grid that mimics the structure of those mesh generating particles. As you can see, you can compare, just in this sort of simple visualization, there's regions of low refinement for the original Arepo mesh, like over here on the left. That's represented on the Flash grid. Same thing here, here, with this higher refinement spine of gas that goes to the center. And then through my Fourier AMR tool, I'll then interpolate data into this empty grid. And we're left with a populated torch grid, which now is usable in our torch computational framework originally taken from you. So it looks very similar to what we started with, which is the point. But yeah, so now we have this file, this data set that we can start from as initial conditions using Torch. And so the question is, though, does this actually work? Like, we get the data there, we know that the data is present, but to know if we've interpolated it properly, one thing we do is just run a simulation. So this is a Torch simulation that is using a repo data that has post-interpolation using my Fourier AMR tool. And so you can see, because this structure is so large, kiloparsecs on the side, we don't see the gas moving around a lot, but gas is collapsing. We are forming sync particles. Those sync particles are forming stars. And the main thing here is that like the system isn't immediately like blowing apart or collapsing in on itself. And so it seems like we're interpolating data properly here. Okay. Yes.
Question. When you do your correspondence between the two systems, that process preserves the number of particles.
Good question. So
That's the next slide.
yeah, that's basically the next slide. Yeah, perfectly then. Yeah, and so the idea, we have those mesh generating particles in the ARRAYPO data, and they are meant to correspond with the data cells of the flash blocks, because the flash, the way it represents data is through those cells, not through individual particles. But we do see some error in this interpolation. So if we're looking at, say, like the total amount of mass of gas that we start with in the ARRAYPO simulation, and then what we end up with post-interpolation of Torch, there is a difference. It's a discrepancy of a couple %. And to kind of understand why that might be happening, we look on the right. I think this visualization will help. On the right, we have, let's say this is representing just what will be one flash block, say a 4x4 flash block. And this is showing the 16 ARRAYPO mesh generating particles within this. So this is our ARRAYPO data. We want to interpolate onto the flash grid. This is what the flash block. This is what the flash block looks like. Each cell pretty much has one data point that is associated with it. And so in the interpolation scheme, each of these cells will get assigned a unique ARRAYPO data point. And so we'd expect the error to be the lowest in this case, essentially 0. But if instead we had a distribution of ARRAYPO mesh particles like this, it's still, at least from Flash's perspective, an appropriate set of particles within a single block. So all Flash knows is the total number of ARRAYPO particles inside of the block. So as long as that total number of particles is 16, Flash thinks this is fine. We can continue with interpolation. But if I try to interpolate, remember each cell only it gets the data from the ARRAYPO data point that is closest to it. So in the case where these points are really clustered down here, only one of these ARRAYPO data points will get assigned to each cell, and we lose some information. So some of those ARRAYPO cells do not get interpolated anywhere, or the cells out here that have no data, no ARRAYPO data in them, they'll interpolate just the closest ARRAYPO particle they can find. And so we get this either smearing effect or this data loss at these sort of clustered points. And so this is due to the interpolation scheme that I use. So potentially this is refinable.
Sorry, why don't you just let it refine?
Good question. Yeah. So the main reason is that, at least for built-in Flash functions, it's able to identify the total number of particles within each block, but it's more difficult, or like some development is going to be needed to take place to be able to identify the number of the distribution of particles within the block, or like the number of particles in each cell. That's something that's a little bit more difficult to find. So yeah, just based off of native Flash functions, this is best I can do. Yeah, that's a good question. Okay. So just a brief comparison between Torch simulation and an ARRAYPO simulation using the same initial conditions. So if we take an ARRAYPO snapshot, convert it to a Torch run, and then evolve both for 3.2 million years, we can look at some characteristics of how the different evolution processes take place. And what we see here, at least for the gas on the right, you can see it's a bit fuzzier than with the Torch run than the ARRAYPO run. Just from time constraints for myself, this was run at a lower resolution than what AREPO is operating at least for the simulation. But the structures look similar. And there's also these star clusters, these black dots or blobs are the star clusters that form. And we can see mainly the point I wanted to make is that star clusters are forming in the same general vicinity. So same general areas we see star formation taking place. We can look at this a little bit closer. It's just, again, very preliminary analysis of preliminary comparisons to some AREPO runs. So what I did is I have two different AREPO runs that, again, are starting from the same initial conditions. One run has stellar feedback present. That's the AW, purple line. One AREPO run has no feedback present. So that's A0. And then I set up 3 torch simulations that that are starting from the same initial conditions as these AREPO runs. But the difference between those torch simulations is that they each have a higher level of maximum refinement that they're able to achieve, so level 4, 5, or 6. In order to achieve the same resolution as the AREPO runs, they'd have to hit level 12 refinement. So they're still under-resolved compared to the AREPO runs, but the main point here is just to illustrate the general trends that we're seeing between these runs. And so there is some discrepancy between the star formation that takes place in the AREPO runs and the torch runs, but the main point here is that we see sort of a general adherence to a trend of increasing star formation over time. These AREPO simulations go on for much longer also, so I think up to 16 million years. So there's more space to evolve these particular preliminary runs more to resolve that. We can also do something, look at the total mass of the total fraction of cold gas that is present in each of these runs. Cold gas being less than 100 Kelvin. So this is really interesting. It sort of shows that my tool, VOR-AMR, presents an interesting way to compare different code bases. So in this case, AREPO and Torch, in the sense that all of the runs are initialized at the same point as they're supposed to. Now, the same total fraction of cold gas present. The AREPO runs then proceed, and there's some changing amount of cold gas as the system evolves. Some gas is able to cool or gets heated up by stars that form, etc. But in the torch runs, pretty much immediately we have this huge spike in the total fraction of cold gas present. So this is implying, or not implying, it's showing that there are different heating and cooling physics modules that we use in torch compared to AREPO. This presents an avenue for which further investigation, I think, is worthy here to investigate truly the difference between these cooling modules, why we see so much gas in the torch run essentially snap cool to a cold state. Again, this is just preliminary analysis. It's just out of these few runs that I have. So I don't have a detailed analysis of this quite yet. So looking at this, there's just as it stands, this ability to interpolate data between a Voronoi mesh and AMR grid, or AREPO and Torch. That in itself is pretty extraordinary. So again, like I said, as far as I understand, as far as I'm aware, that capability did not exist before this work. But on top of this, there's a few other things that my tool can do. One of those is establishing regions of interest, places that we can zoom in on the original AREPO data, and essentially take a cookie cutter, cut out this particular region, zoom in, model the gas there. So I just want to show some quick videos of what that looks like. So we have like region A down here, a little tiny box, or one little cloud, region B and C, slightly larger. We can run these. These are on loops, so they'll loop through and see, or snapshot A is a very short loop. So mainly just showing you can see the gas swirling, stars are forming. In regions B and C, you've got stars forming along the filaments of gas here. Really, all this is showcasing a capability of VOR-AMR, something else I can do. Even more ideally than this is something I'm still actively developing, which is localized refinement. So the issue with the videos I was just showing was that although they look very nice and you can zoom in really close to regions of interest, in doing so, you're cutting away the rest of the influence of that original ARRAYPO data. So looking at a single cloud, maybe in looking at the full ARRAYPO simulation, gas would have been falling into that cloud, forming more stars, or gas flowing out and affecting regions around it. We lose that ability to resolve that behavior and doing just the cookie cutter zoom-ins that we're just looking at. But something like this, localized refinement, really is augmenting the structure of how Flash operates, in that I can define specific regions where I tell Flash, you may only refine in this tiny region, everything else de-refine as much as possible. And this allows us to evolve really small regions of the grid while not wasting or using too much computational resources to resolve and evolve all the rest of the gas out here. We still get the general influences of this outside gas with this region of interest. So gas can still flow in, gas can flow out. We get the gravitational influences of gas moving around. So a really powerful tool. Again, I'm actively working on it.
Okay.
Yes.
If I'm understanding this a little bit, so when you were doing that, you're really saying that denser regions are evolving much faster, so you can sort of use that out of the beginnings.
Essentially, yeah. Or any evolution that takes place here is not very resolved. So we'll be able to see like bulk movements of
So
gas.
it's like a localized wind field. Sort of.
Maybe so, yeah. I mean, yeah, it's really just like we'll have we zoom in like a single cloud and say, this is the cloud that we want to realistically model, or model as realistically as possible. And the rest of that, we want the general influences of.
But then you also limit it in the time scale
Yes.
in which this is.
Yes, exactly. Yeah. So the higher refinement we go, the smaller the time step is required to resolve that the smaller spatial region. Yeah, that's true.
She was asking the opposite. The smaller your region,
Mhm.
the shorter you can run before you start getting influences from the edges,
I'm not sure if
from the unrefined edges.
yeah, I'm not sure if I understand that.
You'll-
Yeah, we'll talk about it in a second. Sorry, yeah. Okay. Great. So we are at the end. Yeah, so let me review the two main components of my work. So the first thing we talked about was the early forming massive stars and their importance in their effects in star cluster formation. So we found that early forming massive stars significantly affect or significantly disrupt the natal gas structure, resulting in premature global unbinding of the giant molecular cloud from which it forms. We find that they suppress the star formation rate and the accretion rate of material onto the sink particles, also reducing the total mass of stars that form. We also find that the early forming massive stars stifle the hierarchical assembly of the star cluster, promoting more spatially distinct and more loosely bound subclusters. We also talked about the numerical tool I developed for AMR, which successfully interpolates data between the moving mesh code ARRAYPO with the AMR adaptive mesh refinement grid torch. We found what this tool represents is it bridges the spatial divide I was describing about between modeling a galactic simulation where clouds can form under realistic conditions there, and the smaller scale simulations that we have run, essentially in effect, eliminating the need to use more idealized initial conditions like spherical clouds or colliding cylinders of gas. It also provides this a new avenue for collaboration between research groups. So now we have a way to take data from other numerical models, model them in Torch, and I'm also in talks with researchers working with a different code, Ramses, which wants to do the similar thing using at least the philosophy of my tool to translate data into there. Future work, there's a lot of work that can always be done with these projects. So the Torch collaboration consists of 8, 9, or 10 graduate students across the world. And there's continuous work that's being done in developing that numerical framework and pursuing some studies there, looking at things like multiple populations, multiple stellar populations in star clusters, higher mass star cluster formation, adding new feedback or adding feedback effects that were previously not present in the model, like stellar jets. And with VOR-AMR, there's also a lot of development that, or future work that can be done with this. A lot of that future work is described in the recently awarded NSF grant, to which I contributed. In VOR-AMR, as I was showing the preliminary results, or preliminary comparisons between the Refinement and Torch, is this new way of comparing numerical frameworks that previously did not exist. And with that, I want to give my acknowledgements to a couple of people. So my advisors and committee, of course, say thank you to my friends and colleagues, both at Drexel and at the Torch collaboration. So friends here, Evan, Steve, Weishang, Prakash, Andrew, original crew, colleagues at Torch, Brooke, Sabrina, Claude, Maita, Eric, Dilhan, Aaron, and Will. I might be forgetting someone, I'm not sure. And I want to say thank you to my family. So my grandfather, my mom, my dad, brother, sister, aunts and uncles and cousins. I think some are on Zoom right now. Of course, thank you to Ashley. Thank you so much. Yeah, I really cannot thank you enough. Like, you are the reason why I am able to be here. Truly, yeah. Thank you, everyone. I'm just kidding. I'm just kidding. Yes, I love you very much. Thank you. And yeah, lastly, thank you to my lovely cat, Brenda. And thank you, all of you, for being a great audience. Really appreciate it.
Okay, we have time for a few questions from anyone not on the.
Great talk, Tom, but
Thank you.
were all these simulations we've seen, were they slices of three-dimensional things, or were they two-dimensional?
Very good question. Yeah, I'm sad that I forgot to mention that. But yeah, these last ones were that's weird. These last ones we were looking at are projected density. So if you took the computational domain from one side and just flattened everything down. Yeah. Good question.
So could you have looked at it from another angle if you wanted to?
Definitely, yeah. So you can flatten any of the X, Y, Z directions. Yeah. And slices too. That's another way of analyzing it for sure. That slices are just more difficult because you have to sort of really pick and choose the region you're interested in. Because like you want to look at a single filament that'll pass through a single plane multiple times. So slicing through that, it bits and pieces of the thing you're looking at. That makes sense. Sure.
I'm curious, when you're creating a sync particle, what is the criteria?
Oh, very good
which
question.
you want to swap over?
Very good question. So there's several criteria. One of which is, I don't want to we'll probably talk about this in the question session after this, but the genes criterion. So it's a length scale at which for a uniform medium gas will continue of certain properties, the gas will continue to collapse. So if that's satisfied, there's also others for self-gravitation, so and infall. So gas will be actively infalling towards the center. There's a few others. I can't remember, but yeah, so there's several checks that need to take place, and then there's even further checks on top of that for the accretion of material onto those sinks. So once those sinks are present, the same sort of thing. The gas needs to be bound to it, infalling.
And then related to that, you mentioned that the main reason to do that is computational. So is there any risk when you make that shift of losing information?
Yeah, so I guess the term in the industry is subgrid physics. So there's a whole resolution only goes so far before you're wasting time. Like it takes too long to simulate. You're looking at a spatial regime too small. But yeah, so in placing a sync particle there, we are effectively erasing the physics that goes on in there in terms of the gas. But the benefit is you have general ideas like the gas, in order to be there in the sink, needs to have been ready to collapse or actively collapsing. So it's likely to be forming stars, and we'll place stars accordingly. But yeah, we do with that are unable to model like accretion disks onto stars within like as before as their pre-main sequence stars. That's all cast aside. Yeah.
So is there an error associated with that discounting you were talking about, especially for the second part? Where you have a density distribution, all of a sudden you go to a different model.
Yeah. You say error associated with this like sync particles.
Or for the second part, when you stop a echo and you use that distribution to start a different simulation.
Yeah, definitely. So yeah, there is error just in interpolating that data between the two. Yes, for sure. And that I think I mentioned like it can be improved. So as you're asking before, being able to identify or assign array data points, data particles to specific flash cells as opposed to blocks. This is something that can be improved. I'm not sure if does that answer your question?
Well, I was thinking more in terms of like you have a density distribution that you just materialized out of thin air as far as your second simulation is concerned. And then you start collapsing the gas clouds.
I see what you're saying.
Is there this continuity?
That's a really good question. Yeah. I think one of the further pieces of further work I think would be really interesting is taking a closer look at the like larger scale and small scale effects post interpolation. And that's something I haven't been able to identify yet, is whether that error is coming from the low refinement regions or the very high. My suspicion is that it's the very high refinement regions that are causing this error, and so that would be the places where you have that discrepancy or maybe weird behavior where that change in distribution or that post interpolation has the same particle that forms immediately, whereas in the array simulation you might have stars that form more gradually because they don't use sinks. Yeah, go ahead.
So I've kind of been thinking about this all along, but we had that last slide about localized refinement. Next to us. And you said, oh, you could do a larger coarse grain simulation of defined in a specific region.
Yes.
So what if you were to expand this to the whole galactic simulation, and then would you be able to prune the outer regions entirely if you could prove that signal couldn't possibly propagate or something like that, and possibly apply a correction?
Sure. Yeah, and I mean similar work like that is being done. So the Arepo model, the galaxy simulation we're looking at, my collaborator Quigley is kind of doing something like that, where it's modeling the entire galactic system. Sort of identifying those clouds of interest, and we'll evolve those separately and reintroduce the evolved distribution back into the galactic model to evolve. But something similar, in principle, could be done with Torch. The consequence with Torch is that it's for the AMR grid, it's less capable in terms of modeling rotational systems. You lose a lot of angular momentum with it. But if you're finding in very closely on a single cloud, you're likely not going through many rotation cycles of the galaxy. So it may not be. But that is interesting. Yeah. In principle, it's entirely possible expanding this to any spatial scale. Yeah. One thing too, I'll just say that's interesting is that for my tool, Vor AMR, it in principle is capable of doing this interpolation with any data type that can be represented as particles. So SPH codes is the other type of hydrodynamic code, mainly hydrodynamic code that's used. That type of data can be interpolated. Other AMR grid codes other than Flash can be interpolated. So it is a very robust framework that can be built upon.
I can't remember if we've talked about this before, but the runs that you do, like in part one of this, for example, like just one fiducial run, when you parallelize that, what exactly are you parallelizing? What's happening on core one versus core two?
That's a really good question. Yeah, so the way, actually this is a good place to showcase that. So the way Flash is organized, Flash, the thing that's handling gas, it'll partition blocks of data to different processors. And then there's several steps that take place where gas is evolved and information is communicated between the processors about gravitational or flow information. It'll several steps like bringing all that back together to transfer data where it needs to be. But yeah, each of these blocks are separate event processors. Torch also, we parallelize the n-body dynamics solvers, so modeling the actual stars. Those benefit from parallelization as well.
Unless it's burning questions.
I'll check the Zoom.
Oh, good point.
Oh, yeah.
Oh, yeah, electrical.
Grandfather.
It's just good jobs, no questions.
Oh. They all say I should get my PhD.
Yeah. Yeah, thank you everyone on Zoom.
Nothing?
Nope.
Next thing.
Yeah, thank you all for coming out. I really appreciate you all being here. Yeah, take some coffee and donuts. There may not be a lot left, but take some. All right, I'm going to turn the Zoom off. So thank you all for coming.
I was here a few months ago, you weren't.
So sorry.
So very good to see you.
Yeah.
I saw Peter.
Bye everyone. Bye.
Oh, yes, yes, I did.
Yeah,
So he's like one of my daughter's good friends at school. Is that, wait, no, Peter.
They are my parents. I'll talk to you guys in a bit. I have to get grilled by my professors.
John.
All right. Bye.